Hello everyone, welcome to the channel. I am incredibly excited to kick off this new highly structured series on real analysis. And I'm designing this three-series course curriculum to provide a clean, deep, and intuitive pathway for anyone who wants to really look under the hood of higher mathematics courses like this one and really see how it works. So I'm sure if you've ever tried to read an advanced math textbook on your own, you already know that it can feel like staring at an unmovable wall of symbols. So my mission here is to really act as your conceptual translation guide, and I really want to break down these profound proofs into clear natural mental steps to serve as I guess, an accessible supplement to deeper, more technical coursework. Um, and if you really want to go into that higher level technicality here in this course of real analysis, I would highly recommend the videos by Mike Dabkowski, known as Mike the Mathematician here on YouTube. His explanations are what transform my own understanding of analysis in advanced math, and I cannot recommend his channel enough to anchor your mathematical journey. So throughout this series, we will be using Kenneth Ross's classical text, which is Elementary Analysis, the Theory of Calculus, as our systematic reference, so that way you can easily cross-reference our video breakdowns directly with the book's sections to study along with us. So today we start with section A, which is why analysis exists. And we're looking directly at a profound historical secret here, which is why calculus, the subject of real analysis, um, is the most successful mathematical tool in history, but also has a very fragile structure, logical structure, for over a century. So before we even get into that, I think we should clarify a couple of things, right? First of all, what even is um, real analysis, right? And I'm sure if anyone has taken the course, has looked into the course, or has just heard about it, has a general idea of what it is. It is the proof-based version of calculus. And in essence, that really is what it is. But I feel like it's hard to grasp that until you really start looking into this course with a more serious perspective. And that's why I want to use this channel as a way for us to explore what that really means. And another thing is another question that's probably more important for you guys is why do we even study it, right? Um, why? And I feel like this video is going to help answer that overall. But I guess like a quick rundown, right, is like I'm sure, for those who aren't going to major into like mathematics, right? Um, it probably doesn't seem as apparent as to why you would even be studying this, right? Like I'm sure if you're an engineer, if the bridge stands, if the rocket is able to fly, that's it. Why do we even need to look at proofs? But I feel like today, because we're looking in today's society, we are building a lot of high tech and more advanced things, right? Like quantum models, all these compilers, all these like fancy things, right? Um, it's especially important to understand the very fundamentals. So in order to continue pushing on not only the higher echelon of mathematics and the frontiers of other fields, we need to really understand the essence of what we're studying. So now that we've kind of had a clear answer, right, we're going to look at an example. So before, like, think about what calculus actually asks us to do, right? If we want us to find the exact speed or steepness of an accelerating curve at one single isolated point of time, right? Um, we'll start with an example here, which is the function f of x is equal to x squared, right? Simple enough. And in order to find that speed in this example, any elementary calculus student should know what to do, right? We take the derivative. So f prime of x is going to equal to x. You just take the derivative, and that is the correct answer. However, let's look at what the more elementary version, right? So think about if we're in the 1600s when calculus is still being invented, right? You can't use these definitions. People are just coming up with these things. So uh, we're going to look at how they figured it out, right? So we look at the work of Isaac Newton, right? So back then, we knew that slope is requiring two distinct points to create a rise of a run. Simple enough, right? We've learned this in our earlier mathematics careers. So obviously, you can't draw a line with just one dot. It requires two distinct points. So Isaac Newton does have a very beautiful proposal to this issue of finding the slope at a single point, which is you're going to be moving x a very, very small distance away, right, h. And now we can take the slope of this curve, right, using this formula. We have, let's see here, x minus h squared minus x squared over h, right? And that is going to be our slope. So if we expand this now, right, we are left with x squared plus 2xh plus h squared minus x squared over h. And we can just cancel out the x squareds, and also conveniently now, right, we can cancel out the h's. So what we're left with is 2x plus h. And so far we've done everything right? So we followed the standard algebra, and we've expanded the numerator, everything like that. But here's the more important thing, right? Because we were wanting to look, we've only looked a very, very small point away, right? And we are only looking at the slope of 1 point. We just set h to equal 0, right? So we're left with 2x now because h is 0. So at surface level glances, right, it does seem correct, but notice the major flaw here, right? If we set h to 0, what we've actually done is divide by 0 because, and obviously that's undefined. So we still have to put the plus h there. So this is the issue, right? What does it really mean if of h being infinitely small? So keep in mind, we're still in the 1600s. There's no explanation for this. So engineers use this to build things. Economists use this to optimize portfolios. But we've just committed a massive mathematical crime, and people don't know how to fully explain this. So in order for mathematicians to protect this, they come up with this definition here, right? And that is calling h to be infinitely small. So they coined the term for this as an infinitesimal. So basically what they're saying is if you want h to be canceled out, right, it's technically a value that is infinitely small in the sense that it's greater than 0, but very small in the sense that it is less than any positive real number. And also, if you want it to be gone, it can suddenly act like 0. So this, I guess, dual personality is ultimately what led to this famous, I guess, description of it by this prominent philosopher at the time named George Berkeley. And he criticizes mathematicians for this direct flaw and calls these things the ghosts of departed quantities. So like I said earlier, they're not quite 0, but they weren't non-zero either. And for more than a century, humanity's, I guess, scientific triumphs and continued innovation is all being rested upon by a paradox. So this level of fragility is what ultimately leads mathematicians to realize that they're relying they're relying on intuitive luck, and this is very unsustainable. So if their foundations weren't completely secure, deeper extensions of mathematics would eventually fracture. So now there's a, I guess, direction in the opposite way of looking and truly understanding the very fundamentals. And this is what leads us to the, I guess, four foundational layers that we're going to look closely at. The first being the real numbers. Um, the second being, I guess, ironclad limit definitions, um, including things like epsilon and delta. We'll look about what these are in other videos. Three, which is rigorous continuity and convergence. And finally, stricter definitions of derivatives and integrals. So, the exact historical rescue mission of mathematics is why the field of real analysis was born. So, real analysis, in essence, is the meticulous process of rebuilding calculus from the ground up and ensuring every single definition they've came up with is completely bulletproof without justifying and defending it with these fragile terms such as the infinitesimal. So we do this by throwing out fuzzy shortcuts, like I mentioned earlier, the infinitesimal, and replacing them with the precise concept called a limit. But as pioneers of analysis began this reconstruction, they bumped into an even bigger obstacle than the disappearing numbers. And then they realized that to define a limit clearly, they had to confront the most counterintuitive concept of all, which is going to be infinity. And in our next video, we're going to explore how the crisis of infinity breaks our ordinary rules of logic in mathematics and look at the paradoxes that pushed early mathematicians to the absolute brink of insanity. So our next video is going to be the crisis of infinity. So I'll see you in the next video, and thank you for watching.